All right. This is just going to be a recap of what we were doing on Thursday before everything happened. All right. Hope everyone's doing well out there, by the way. So this was the experiment we did where we were taste testing Skittles to see if there really is a difference in color. And one thing important to establish right now is that if there's no difference in color and there are 5 different flavors to pick from, then just randomly guessing, we should expect about 20% of the correct answers, 1 in 5, to be right. So if there really isn't a difference in the flavors, then the true proportion should be about 0.2. Again, that's just by random chance how many you'd expect to get right. So we're going to test that idea. Now, the data that we collected that day, and in future lessons that I post, I'm going to make up data, but we actually did this one. So 84 correct guesses were made out of 120, and when you do that math, that is, our p hat was 0.7. I guess I could have put that down here. But okay, so we're going to use that in our test, and I'll name that in just a second. But before we do that, we are basically hypothesis testing. And I should also mention here at the beginning that the main thing that we're doing here is we're creating this framework, the state, plan, do, conclude framework, because that kind of follows the free response format of the AP test. So the parameter here is P, which in this case is let me do this in a different color, the true proportion of correct responses, of correct guesses. And what we're doing with our hypotheses is we're going to have the first one is the null hypothesis is always that the proportion is equal to, or equal, it can be greater than or equal to, but it always has to equal that the true proportion equals what we hypothesize it to be. So, assuming that there is no difference in the, sorry, I'm having a hard time thinking, but assuming that there's no difference in the flavors, then the true proportion would be 0.2. The alternative hypothesis is that, well, we think that there is a difference in flavor, and so therefore the proportion will be higher. And we're going to specifically state that we think it's higher than 0.2, because people can tell the difference between cherry and, sour apple. Okay. And our significance level is given here, but 5%, the 0.05 alpha, is a fairly standard one, and you're aware of that by now. The name of the procedure here, again, this is all repeat, so you have this written down probably. It's the one sample z-test for P, which is, your population proportion. Now, an abbreviation for this is a one prop z-test. So if you, in fact, on your calculator, and I don't want to explain how to do this just yet, but on your calculator you can do this in a very fast way. But for AP purposes, we don't want to do it just really quickly on the calculator and write down an answer. You probably understand that. But in your calculator you can find a one prop z-test. And so that's kind of a shorthand people refer to it as. Now, before we can do this, we need to make sure we can actually even do an analysis. And we need to check our conditions. The conditions here is that, well, is it random? Hopefully you guys remember this stuff well enough. We always check the randomness, and this is just basically looking at how the testing was done. We did this, we know that we randomly selected. So yeah, we randomly selected. So I'll just put a check mark, but you can explain that. Of course, you'd want an explanation. The 10%, this says that the fact that we sampled without replacement, I really hope we didn't replace these Skittles after we tasted them, that the 10% condition, the fact that we are sampling without replacement, doesn't throw off the results, and we can still use our standard deviation and all the other formulas. So yeah, 150 is, sorry, not 150, 120 Skittles is definitely less than 1/10 of our total population. And the last one, of course, is normal. We need it to be normal so that we can use our what we learned about sampling distributions. And yeah, we use for proportions, that means large counts. I'm having to rethink through this stuff too. I've had my spring break as well, so large counts, you'll remember that, of course. So n times p, and then n times 1 minus p, both have to be greater than 10. All right, both of them have to be greater than equal to 10. That can be equal to. And yeah, here if we do that, we had 120, and then 0.2. So it's by the 0.2 that we hypothesize at. 120 times 0.2 is, well, what is that? It's going to be 24. So yeah, we did that. So we're good. And then 120 times 0.8 will be, I can't do math very quickly here, but it's going to be 96. Okay, so we're good. And it's just important to show those calculations. It's not too difficult to do that. All right, so now the do. We have our general formula, and whenever we were coming up with a general formula for a test, we always use what's called a test statistic. And the test statistic is basically your z-score, but we don't call it a z-score here. And so we take our statistic that we calculated from our experiment minus the null, and we divide that by our standard deviation. All right, so the specific formula here, because we're dealing with proportions, and this is just a one proportion test, our z is going to be our p hat, which is the statistic that we found, minus the p that we are assuming as true. Then we're going to divide it by our standard deviation formula, which you'll recall is p times 1 minus p divided by n, and then the square root of all of that. Okay, and then this is where we had to do the work. So you want to show this. Again, it's just to show that you know what you know. And the work here. So if I have my p hat, all right, my p hat, if you remember, is 0.7 minus the proportion here is 0.2. Again, this is one that we could just look at and determine that this is false, but it's more important that we show the process and we understand why the null hypothesis should be rejected. All right, so let's go through this. We have a 0.2 times 0.8, 1 minus p, divided by n, and n in this case was 120. And when we do that math, I'm going to pause right here so I can do that math. Never mind, we'll just kind of work through it here. So you know it's going to be 0.5 divided by square root of 0.16 divided by 120. And then 0.5 divided by, and now is where I'll do the math. So I've got my calculator up. All right. And then I'm just punching in the square root of that real quick. Okay, we're going to get 0.0365 right there. And we do that division. and we get, this is where we got that really, really incredibly strange number, about 13.7. And honestly, something that big, we don't even need to worry about the decimals a whole lot. I got 13.693. And remember, I used the actual full decimal in my calculator and got the 13.693. If you just used 0.0365 and rounded at the end, and you got close to that number, AP readers are not going to squibble over something like that. They just want to make sure you know what you're doing. But do have some degree of precision as you're doing your work. All right, 13.7. So let's draw a picture and really imagine what this is saying. We have a normal distribution. We're imagining a normal sampling distribution of a proportion. And the mean, remember, is going to be 0.2. The sampling, the standard deviation here is going to be about 0.0365. So we're going to have 0.2365, and then 1 minus that is going to be 0.1635 right here. And anyways, and it goes on from there. So our mean is 0.2, and standard deviation is 0.0365. That's our normal model. And we're saying that to get 7, or 0.7, that's going to be, and if you remember, we showed this in class. This is the number of standard deviations away. On my paper, I can only fit 1, 2, 3, 4, 5, 6 standard deviations. So it's way over here. And so we're looking for the area to the right of that. And so basically, it's a very, very low probability. And so our, we can just see, this is why kind of this test is a little bit redundant. We don't need to show it, but of course we do need to show it. Okay, so the test statistic was Z is 13.7. Now your p-value, this is basically your normal CDF. And we have a normal model, and we standardize this to a z-score. So now when you're using your normal CDF on your calculator, you just want to look for the tail to the right of a z-score of 13.7. And it's going to be ridiculously small. In fact, we looked at that. Now I'm having to remember where to get that. There it is on the calculator. So 13.7 is my lower bound. My upper bound is going to be something really big. And this number is just so ridiculously small. In fact, you can double check my math. I'm getting a very wild number here. I don't remember it being that small in class, or being quite that in class, but anyways, hopefully the math, the process is making sense. If I made a calculation error along the way, hopefully you can catch that. But that is, and the main idea is this p-value, to this number right here that we just calculated, is this smaller than our alpha? It's fair to say that yes, it is. Our alpha is 0.05. That's definitely smaller. So this is the conclusion we can make based on that. And we kind of have our formula for how to say this. We do have convincing evidence to reject the null hypothesis. Okay. And then we could add context in there. We can say we have evidence to suggest that Skittles are different flavors. Now, we do have to be careful with that. I don't want to say too much on that point because we don't want to make a claim that would, a reader would look at and say, you went beyond what the statistics support. So, as long as you use the framing of the question according to how it was presented, then you should be in decent shape for that. So don't try and formulate the words yourself. Just look at what the question was in the prompt and just use the same language. Okay. So that's what we did in class. And the important ideas here is that state, plan, do, conclude. So I'll just write it in real quick. State here is your parameter, your stat, your hypotheses, and your alpha level. Plan is the name of the test, so name of test. In this case, it was the one sample z-test for proportions, name of test, and your conditions. Check your conditions. Do. This is where you show your work, but you need your general and specific formulas. You have to have your picture and your work. And then the answer. And when we say the answer, that means we have a test statistic, which is the stat minus the null all over the standard deviation. And you need to have your specific, which here is z equals p hat minus p divided by square root of p minus times 1 minus p all over n. And so the answers, we actually need to make sure we very clearly show that. And then conclude. Here says we do or do not have convincing evidence, and I'm going to put ... And then the main idea is, I'll just add this also, reject the null. We can or we can't reject the null. We never accept the alternative hypothesis. We either accept or reject the null. Okay. And hopefully, again, like I was saying at the beginning, this is just recap and you're saying, okay, yeah, now I'm remembering everything we were doing. Because you've had spring break and lots of other things to think about since then. Now, we do have, and we wrote this down, but we didn't talk about it, so this will be the little bit of stuff that's going to be kind of new. But we have a two-sided test. So in our sample here, we were only curious to find out if our proportion, our p hat, or sorry, if the true proportion was greater than the null hypothesis. We were only curious about that. We didn't think it'd be lower, but we thought it could be higher. Because, and again, the reason we weren't worried about being lower is because if we have 5 flavors and we're testing, by random chance, we should get 20%. So it's unlikely that it would be lower. But if there is a difference in the flavors, then the proportion should be higher. We're only interested in our true proportion being higher. But if it's a different situation where we don't know if it's higher or lower, we might want to just test both. And all we have to do here is multiply the p-value by 2. And I'm going to do a sample of that real quick. to show you how that's done in practice. Because you remember your p-value was saying we found the area under the curve at the high end of our normal curve, and it was a very, very small number. If we had said, well, okay, it could be higher, it could be lower, well, then we could take that p-value and double it to show that it could be on the very low end of the tail. It wouldn't have made a lick of difference in this example because of how small that p-value was. But in some cases, it can. Okay, so let me see real quick. Let's examine this next example. According to the National Institute of Occupational Safety and Health, job stress poses a major threat to the health of workers. A news report claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. Managers of a large restaurant chain wonder whether this claim is valid for their employees. A random sample of 100 employees finds that 68 answer yes when asked, does work stress have a negative impact on your personal life? Okay, so there's the setup, there's the prompt. Do these data provide convincing evidence at the alpha equals 0.1 significance level that the proportion of all employees in this chain who would say yes differs from 0.75? Okay, now this word right here, what you might see in your prompt, if it says is greater than or less than, then of course that's telling you what your alternative hypothesis is going to be. But if we're saying does it differ, that means we're not sure if it's higher or lower. So this word right here is kind of a keyword indicating that we're looking at a two-sided test. And again, that'll be, I'll come back to that in just a second, but let's kind of start going through the four-step process. We've got a parameter. So what we're looking for is the true proportion of employees of employees who say yes. The statistic, well, you see in there that there were 68 out of 100 who said yes. So 0.68. So far, so good, I hope. Our hypotheses. We have the null hypothesis, which is that the true proportion is exactly what that estimate was, 75%. 75%. So let me write that as 0.75. Our alternative hypothesis is not going to be that p is greater than or less than. Our alternative hypothesis is that the p does not equal 0.75. Okay. And so it could be 0.85, it could be 0.65, it could be any other number. We're just saying it's not really 0.75. And the significance level here, they gave us an alpha of 0.1. The name of the procedure, we're not learning anything different, so it's still the one sample z-test. For proportions. Conditions, random. Let's read did it say that they randomly selected their employees? There it is. So it's right there, a random sample. So yeah, we've got that. Is the 10% condition met? Well, let's read the prompt. So it says a large restaurant chain and a random sample of 100 employees. If it's a large restaurant chain, I think it's fair to say that yes, we've met that condition as well. And the last little bit, the large counts, so normal. So remember, we're using the proportion that's given as the one we're testing, that 0.75. We sampled 100 employees, so 100 times 0.75 is 75. We're good there. 100 times the complement to that is also good. So yeah, we've met large counts. All right, general formula was our test statistic. Which is, don't have a lot of space here, so I'm going to put the stat minus the null over the standard deviation. And our specific formula here was that our z equals p hat minus p all over square root of p times 1 minus p divided by n. The picture, well, I'm just going to get started. We don't have the numbers yet to fill this in, so I'll just start off with the picture. Let's do the work and then we can fill in the picture. All right. So our z score right here, our stat was 0.68 that we got from the sample, the 0.75, and now we're going to calculate this out. So you got 0.75 times 0.25 divided by n, in this case was 100 employees. Okay, and we can start doing that. And you guys can do that math. In fact, if you want to pause along the way as you're doing these videos, I should have said that at the beginning, so that you can kind of do this work on your own, and then you can kind of test, make sure you did it right later, you can. Anyways, you had time to pause. The answer here is going to be negative 1.63. Okay, at least it should be. Actually, negative 1.62 is what I got. Okay, so your test statistic is negative, well, let me write z equals negative 1.62. And that negative 1.63, you could get that if you round it ahead of time. So anyways, now we're ready for the picture, and we already knew, I'm going to have to squeeze this in, that 0.75 would be the mean of the sampling distribution, and I'll just write down here that our normal in this case is 0.75 with, when you calculate the standard deviation in the work before, you should have got 0.043, and there it is. We are looking, because we're not sure if the true proportion is higher or lower, we're going to do a two-sided test, which means we want to test both the low end of this and the high end to see if it's possible that a number like this could have appeared in that case. And so what we want to do is double our z-score, or double our test statistic, or double the p-value, I'm sorry. So let's find the p-value, and then we're going to double that value. So don't double this. I misspoke a second ago. That'll throw off your answer. All right. So we're going to do normal CDF on the calculator. Okay, and after doing that on the calculator, I was able to get 0.0526. I'll just write it out. 0.0526. If you did a negative 1.63, depending on your rounding and everything, your number should be close to that. Now, this is just the probability that, or let me say it this way. This is the area under one of the tails. We want to get the area under both tails, so I'm going to double this, I'm going to multiply by 2. So in my case, it's going to be 0.1052. And when I get that, I have to compare, is this less than the alpha value that I set of 0.10? No, it is not. So therefore, we can't reject the null hypothesis. So we have that formula up above that says we have or do not have convincing evidence to reject the null hypothesis. And then we can expand on that to provide some context. I'll give you another phrasing here. So, assuming the proportion of employees who answer yes is 0.75, there is a .105. What did I get? 1052 probability of getting a sample proportion as far as 0.68 or further, meaning it could have been an equal distance up above, purely by chance. In future videos, I'll try to just write stuff out and then just provide the commentary. So, we fail to reject the null. Okay, so that's obviously a lot more writing. It's providing some context, and it's taking some of the phrasing from the prompt itself, just as far as the how we've kind of set it up. And anyways, we're including all of our data in there. Not all the data, but all the conclusions that we came to, all the p-value. And, I wish I could tell you exactly the way you need to write this every single time. But hopefully you're kind of getting a good feel for it as you're doing more and more of this. So the very last one of these, luckily we don't have to construct the confidence interval, but the confidence interval for 90% for this particular data was found to be, and you can see the numbers right there. So explain how this confidence interval is consistent with but gives more information than the test. So just talking about it for a second, you can see that 90% confident that the true mean lies within that interval right there, or the true proportion falls within that interval right there. You can see it goes all the way down from about 60% up to about 76%. And we got 0.68 in our sample. So then let's think about this. If we're 90% that it falls within that interval, and that 0.75 falls within the interval, well then, and this was the confidence interval from the 0.68 as the p-hat. That's where we created it from. So this confidence interval is consistent with that because the 0.75 falls within the interval. Okay, so let's kind of, here's a sample answer to this one. The null value of 0.75 is included in the interval. So it is plausible. the interval also gives other plausible values for the null. So that's what is interesting here. So just to provide some commentary on that, if at the beginning we were looking at this, you're like, well, it's 0.68. Why are we testing two-tailed? We don't know if it's high or lower, sure, but we got 0.68. Okay, so this provides a little bit more context here. So the interval gives plausible values for the null, which according to our sample, when we got 0.68 proportion, the only plausible values, now it could be with outside that 90% confidence range, it's definitely a possibility, a 10% probability, but you know, anywhere between 60 and 76%, those are possible places where the true proportion to lie. So 0.75 is plausible, but we can start guessing that something like 0.85 is not. And of course, the way we could hone on this more is if we did more random samples and got more confidence intervals, and we could hone in on what the what that true proportion might be. So hopefully you can kind of see the difference between the tests that we can do and the confidence intervals, where the test is basically saying, hey, here's something that's been thrown out as the true proportion. Find out if that's plausible based on this sample. And the confidence intervals are saying, here's just some random samples. Let's kind of, using inference, come up with what the true proportion might be. And different ways of kind of seeing, not the same thing, but similar types of problems can be answered. And anyways, hopefully this was not too confusing. I do want to try and make these videos shorter in the future, so anyways, give me any feedback if you have questions, something you didn't understand, and maybe I didn't clarify something well enough in the video. And just like I kind of wrote on the Google Classroom, make sure you're checking periodically to make sure to see if anything new is posted. All right, I'll see you guys eventually, hopefully.